AC circuit concepts for purely capacitive circuit. So remember Ohm's law, V equals IR. Then if the voltage and current are out of phase, so we have here impedance Vm angle P over Im angle theta, where the angles or the phase angles are not the same. We have this expression, okay, for the capacitive circuit, the difference between the angle of your voltage and current are negative, okay, or the phase difference is negative, okay, less than 0. Okay, so that's what we call impedance equals resistance minus J capacitive reactance. Now for a purely capacitive circuit, there's no resistance, okay, so resistance is equal to 0. We call the purely resistive circuit, the difference between the angle of your voltage and current is equal to 0. So therefore the capacitive reactance or the reactance in general is equal to 0. Therefore your impedance is equal to Z, or so your impedance is equal to the resistance. But for purely inductive circuit, so they're totally out of phase by 90 degrees, or the difference between the angle of your voltage and current is 90 degrees. Okay, so therefore we have here the inductive reactance XL is equal to WL, or the angular frequency times the inductance. Okay, and you have the impedance equals to JXL. So that's for the purely inductive circuit. But for capacitive or purely capacitive circuit, the difference between the voltage angle and the current angle is equal to the negative 90 degrees. So we would like to introduce to you XC. So that's equal to 1 over angular frequency times the capacitance. Therefore, we have the impedance is equal to negative J XC, okay, where the resistance is also 0 in this case. Okay, so to illustrate the concept, we have here a circuit where we have the instantaneous values for your voltage and current, and if you notice, this is our capacitive reactance. Take note, in the circuit there's no resistor, there's no inductor, therefore this is a purely capacitive circuit. And then your capacitor there is expressed by negative J 1 over angular frequency times the capacitance. So we will discuss capacitance in other lecture in electromagnetics. So here we have a signal for your voltage source Vm amplitude, and then you have here your Im. Initially they are in phase, so this is actually a resistive circuit. But for a purely capacitive, so the current is leading the voltage by 90 degrees. Okay, so take note that the current is leading the voltage by 90 degrees. Compared to the inductive circuit, the current is lagging the voltage by 90 degrees. So here it leads by 90 degrees. Okay, so we have here the Ohm's law. Impedance is equal to the voltage over the current. Now if you look at the Phasor diagram, you see that your Im is 90 degrees leading the voltage. Okay, so in the previous video we said that your voltage may not be in the 0 degrees, okay, but as long as they are 90 degrees. So we have here Vm angle 0 degrees. Most of the time, most of the books, they will use the voltage, they will most of the time make the voltage angle 0 degrees. Then you have the current 90 degrees. So they vary the current instead of the voltage, which is most of the time the case for the power system. Okay, so if you perform the basic complex number operation, so division in this case, so we have this polar form equivalent. So then we have Zm, or the magnitude of your impedance, okay, which is equivalent to the quotient of Vm over Im, or the magnitude of voltage over the magnitude of current. Then the angle is negative 90 degrees. Then if you're looking for the rectangular form, then you will see that there's no resistance, or in this case there's no real number. So here in this side, so that this becomes 0, so therefore we only have a complex or the imaginary number xc. Okay, so the xc here is equal to, or the reactive capacitance is equal to the 1 over angular frequency times the capacitance. So therefore you have this expression for your purely capacitive circuit. So the total impedance is equal to Zm angle negative 90 degrees for polar form, and then for the rectangular form you have 0 minus J1 over Wc. Okay, now I would just like to remind you that the angles in the circuit depends on the starting point. So not all the time the voltage is at 0, but if you have the difference between the voltage angle and then the current angle is equal to 90 degrees, then we can call this one purely capacitive circuit. But as a rule of thumb, okay, as a rule of thumb, we treat voltage, or the angle of your voltage, equal to 0 degrees, such that it would be easier to solve and also to illustrate the Phasor diagram as you can see in this presentation. That's it for purely capacitive circuit.